In 1997, the Pacific Ocean did something no one was fully prepared for. Sea surface temperatures climbed to levels that shattered every historical record. Monsoons failed across entire continents. Wildfires consumed millions of hectares. Floods killed thousands. The global food system buckled. Scientists called it the El Niño of the century. Then, in 2015, it happened again, a second monster event that drove global temperatures to their highest point in recorded history. Now, in 2026, the Pacific Ocean is waking up. The warning signs are already in motion. The water is warming beneath the surface. The winds are changing. Climate agencies from NOAA to the European Center for Medium-Range Weather Forecasts are issuing alerts that the world hasn't seen since before those catastrophic events. This isn't speculation. This isn't a fringe forecast. This is what the data is showing right now. And if the models are right, the world may be facing a Super El Niño, unlike anything seen in over a century. To understand why this matters, you need to understand the machine. The Pacific Ocean is not passive. It breathes, it cycles, it redistributes heat in patterns that have shaped civilizations for thousands of years. Under normal conditions, powerful trade winds blow westward across the tropical Pacific, pushing warm surface water toward Australia and Southeast Asia. Cold, nutrient-rich water rises along the coast of South America to replace it. Rainfall patterns across the globe organize themselves around this balance. El Niño breaks that balance. When trade winds weaken for reasons still not entirely understood, warm water that had been stacked in the western Pacific begins to surge back eastward. Sea surface temperatures in the central and eastern Pacific rise dramatically. The atmospheric circulation above responds. The entire global weather system reorganizes itself. Droughts appear where rains once fell. Floods surge where land was dry. Hurricanes shift their paths. Wildfires intensify. And the global average temperature climbs not from greenhouse gases alone, but because billions of tons of stored ocean heat are being released into the atmosphere all at once. This is El Niño. It is natural. It has happened for millions of years. But in 2026, it is not arriving into a neutral world. Right now, beneath the surface of the Pacific Ocean, something is building. Oceanographers have been tracking a series of Kelvin waves, enormous pulses of warm water traveling eastward along the equator at depths of up to 200 meters. These are not small fluctuations. They are continent-scale movements of heat, and they are one of the most reliable precursors of a major El Niño event. Simultaneously, trade winds across the tropical Pacific have been weakening. When trade winds lose strength, warm water can no longer be held in the west. The system begins to tip. Sea surface temperatures in the central Pacific are already running above average. And buoy networks measuring subsurface heat content are registering anomalies that climate scientists describe as, and I'm quoting directly here, reminiscent of conditions in early 1997. That last point deserves a moment of silence. 1,997 produced the most destructive El Niño in modern recorded history. NOAA's Climate Prediction Center has assigned a high probability to El Niño, developing and strengthening through 2026. European climate models are in agreement. Some ensemble runs where multiple model scenarios are averaged together are indicating this event could reach the threshold classified as very strong, or, in the language beginning to circulate among forecasters, super. To understand the stakes, consider the two most recent benchmarks. The 1997 to 1998 El Niño is the standard against which all other events are measured. It caused an estimated $16 billion in global damages. Over 2,100 people died in floods and landslides in Peru alone. Indonesia experienced its worst drought in 50 years. Wildfires across Borneo burned for months and released more carbon into the atmosphere than all of Europe's industry combined that year. East Africa flooded. Northeast Brazil dried out entirely. Coral reefs bleached on a global scale for the first time in recorded history. Then came 2015 to 2016, a second super event. Global average temperatures in 2016 set a new all-time record. The Amazon experienced extreme drought stress. The Great Barrier Reef suffered the largest bleaching event ever documented. Food crises deepened across sub-Saharan Africa and Central America. Glaciers retreated at accelerated rates across 3 continents. Each of these events unfolded in a world slightly warmer than the one before it. The world today is warmer still. The baseline has shifted, and the next event, if it arrives at the intensity current data suggests, will not simply repeat history, it will exceed it. Climate scientists are careful people. They don't make headlines lightly, which is precisely why the current tone of their communications is significant. If El Niño develops as current models suggest, the cascade of consequences would be extensive. Across South America, particularly in Peru, Ecuador, and parts of Brazil, extreme rainfall and flooding are the primary threat. These are regions where infrastructure is already strained and where a major flooding event in 1998 required years of reconstruction. In Australia, Indonesia, the Philippines, and southern Africa, severe drought conditions would emerge. These are breadbasket regions. Agricultural systems that depend on monsoon reliability would face disruption at scale. Livestock, groundwater reserves, and crop yields would all come under simultaneous pressure. California and the American Southwest could see above-average rainfall, which sounds beneficial in isolation. But when delivered in compressed bursts to fire-scarred terrain with poor water absorption, it frequently produces destructive flooding and landslides rather than meaningful replenishment. In the Atlantic, El Niño conditions tend to suppress hurricane activity by increasing wind shear, an atmospheric effect that prevents storm systems from organizing. This may offer some relief to the Caribbean and Gulf Coast. In the Pacific, the opposite is true. Conditions favorable for typhoon and cyclone intensification increase sharply. Japan, the Philippines, parts of China, and Pacific Island nations face elevated risk. The disruption does not follow borders. It does not respect economic status. It lands everywhere, simultaneously, and the regions least equipped to absorb it are typically the first to be hit. Perhaps the most consequential dimension of a Super El Niño is one that rarely makes headlines until it's already too late: food. The global food system operates on thin margins. Production is geographically concentrated. Monsoon-dependent agriculture in South Asia, East Africa, and Southeast Asia feeds hundreds of millions of people. A single failed growing season in any one of these regions triggers price shocks felt across the entire global supply chain. In a Super El Niño year, it is rarely just one region. The 1997-98 event disrupted harvests across multiple continents simultaneously. Rice production in Indonesia collapsed. Wheat yields in Australia fell sharply. Maize output across parts of southern and East Africa plummeted. The cascading effect on food prices contributed to social unrest, malnutrition crises, and long-term economic damage in some of the world's most vulnerable nations. The 2026 event would arrive into a global food system already under stress from recent years of climate extremes, energy, volatility, and geopolitical disruptions. The compounding effect of a Super El Niño on top of existing fragility is precisely what concerns agricultural economists most. This is not a distant problem. It does not stay in the fields. It arrives at the checkout counter. It arrives on the plate. Beyond human systems, the natural world would bear an enormous cost, and unlike economies, ecosystems cannot be rebuilt with emergency spending packages. Coral reefs are the ocean's most climate-sensitive ecosystems. They bleach when sea surface temperatures rise even slightly above their tolerance threshold, and El Niño-driven warming in the tropical Pacific is precisely the kind of rapid temperature spike that triggers mass bleaching. Events. The Great Barrier Reef has already undergone multiple bleaching events in the past decade and is operating in a severely weakened state. Another major bleaching event could push entire reef sections past the point of recovery. The Amazon rainforest, which functions as one of the Earth's most critical carbon sinks, experienced drought conditions in 2015-16 that reduced its capacity to absorb CO2 and increased fire risk across large portions of its canopy. A similar or stronger drought in 2026 could produce a forest that emits more carbon than it absorbs. That is a tipping point scientists have warned about for years. It may now be within range. Fish populations in the eastern Pacific, particularly anchoveta off Peru, collapse during El Niño events as cold, nutrient-rich upwelling is suppressed. The anchoveta fishery is one of the largest in the world by volume and underpins global fish meal production used across aquaculture and agriculture. The cascade runs deep, deeper than most models capture. Here is the critical distinction that separates 2026 from 1997. El Niño itself is natural. It is a feature, not a flaw, of the Earth's climate system. It has occurred on roughly 2 to 7 year cycles throughout human history and long before. But El Niño does not operate in isolation. It operates on top of a baseline. And the baseline has shifted. Global average temperatures are now approximately 1.3 degrees Celsius above pre-industrial levels. The oceans have absorbed more than 90% of the excess heat trapped by greenhouse gas emissions over the past century. The atmosphere holds more moisture. Sea surfaces are warmer before El Niño even begins to add its own heat signature. This means the same El Niño event, the same wind anomaly, the same Kelvin wave, the same oceanic temperature shift produces more extreme outcomes in 2026 than it would have in 1997. The foundation it builds on is already elevated. Scientists call this the compounding effect, natural climate variability amplified by anthropogenic warming. The ceiling has been raised, and El Niño is about to test exactly how high the new ceiling goes. The Pacific Ocean does not negotiate. It does not respond to policy. It does not pause for elections or economic cycles. It moves according to forces that dwarf anything human civilization has produced. But civilizations do respond. They monitor. They prepare. They adapt. The difference between a catastrophic event and a manageable one is not whether the event occurs. It is whether the systems designed to protect people, early warning networks, food reserves, disaster response infrastructure, international cooperation, are positioned and funded before impact, not after. The window for that preparation is now. The Pacific is signaling. The instruments are reading. The scientists are publishing. Whether the world is listening is a different question entirely. If this kind of deep dive science content matters to you, subscribe. Every subscriber directly supports more of this work, and it keeps this channel independent. Drop your thoughts in the comments. Have you personally lived through an El Niño event? Where were you, and what did it look like on the ground? Tell me your story. I read every single one. And stay for the next video in the queue. It covers another planetary boundary most people have never heard of, one that connects directly to everything we just discussed. It's already there, waiting for you.